Now let's look at an optimization problem that starts off as a word problem. Here we want to build a box that is twice as wide as it is deep, and we want the surface area to be 144 square feet. And the question is, what dimensions maximize the volume? Okay, so what we're going to want to do first is to try to take the word problem and kind of translate it into just sort of a pure math problem. So it's often helpful to draw a diagram of the situation. Here we're building a box. And a box has three dimensions. You might look at its depth, and its width, and its height. Of course, I can call those dimensions whatever I want to. Some people might use x and y and z. And so our goal is going to be to translate everything to be in terms of these variables, width and height and depth. So let's just go through. So we've taken care of this first half. We want to build a box. Great, I drew a box. We want it to be twice as wide as it is deep. So what that's saying is that I want for the width to be 2 times the depth. So let's go ahead and just cross out width and write 2d here. So now we're down to just two variables, d and h. We want the surface area to be 144. So what's the surface area of a box? Well, for a box, it's nothing fancy. A box is bounded by 6 rectangles. They're the 3 you see here, the front and top and right, and then they're sort of mirror images. So in general, what happens is you get either 6 areas or sort of 3 pairs of areas. So in this case, the front plus the back, the front and back are both 2d across by h high, and so the front and back are both 2dh. Then we have the left and the right. Those are both d by h. And then we have finally the top and the bottom. And the top and the bottom are both 2d by d, so 2d squared is the area. And so putting that all together, we get that the surface area ends up being 6dh plus 4d squared. So that's the thing that we want to be 144. And now the question is, what dimensions? So that's asking basically to find, in this case, d and h, maximize the volume. Well, the volume of a box is the product of its width and depth and height, or x times y times z, or whatever you labeled those as. And since the width was 2d, I just get 2d times d times h. So in our case, 2d squared h. Okay, so we want to maximize v. So you'll know that you've done a good job of translating everything if you could at this point just completely erase or cross out all of the words and still have everything that you need. And if you can't, well then it's worth trying to sit down and actually finish translating everything into math in kind of the very first stage. Okay, so now we're down to sort of a pure math problem, and now this is roughly speaking in the same form that we saw last time. I want to maximize v, so that's my objective. I need for 6 times dh plus 4d squared to be 144. That's my constraint. So let's do what we always do now. We're going to solve the constraint for one of the variables. So for d or for h. Well, in this case, our constraint equation has h in only one spot, which is going to make it much easier to solve for h. So if you just subtract 4d squared from both sides, we get 6dh is 144 minus 4d squared. And so h is 144 minus 4d squared all over 6d. And now we're going to plug that into the objective. So the objective function, remember, was 2d squared h. So that's 2d squared times 144 minus 4d squared divided by 6d. And it's worth simplifying at this stage because in a minute we're going to take the derivative of all of this. So d squared here out front and d on bottom, I can cancel out one of those d's with this one. And this 2 here and that 6 there, well, I can cancel out that to put a 3 there on bottom. So I'm left with a d on the outside and all this stuff on the inside. So I have d times 144 minus 4d squared over 3. And if I distribute the d and also the over 3, you end up getting 48d minus 4/3 of d cubed. Okay, so that's what I will call f of d. That's our objective. Okay, now what do we do next? I want to find the critical points. So we set f prime equal to 0. So f prime is 48 minus 4d squared. And if that's going to be 0, well, that means I want for 4d squared to be 48. And so d squared is 12. And again, in principle, d then would be plus or minus the square root of 12. But d is a depth, right? It's a dimension of a box. So clearly we want only the positive solution here. So I get the square root of 12, or what you might prefer to write as 2 times the square root of 3. All right, now let's test that critical point. So we're going to test the critical point using the first derivative test. Remember what that means is we're going to take our critical point, put it on a number line. Again, since d is a depth, there's actually a clear lower bound. Clearly, we don't want any depth less than 0. And so now I look at f prime, which again is over here. So f prime of a number that's just a little bit bigger than 0 is going to be positive, whereas f prime of a pretty large number is going to be negative. So f is increasing and then decreasing. So that means that I do get a local maximum at d equals 2 root 3. But then remember our argument from before that whenever you have a continuous function, and f is continuous, f is just itself a polynomial. If you have a continuous function on an interval that has only a single critical point, and that critical point is a local maximum, well, in fact, that must be the absolute maximum. Okay, well, we're almost done, so we just have to remember what the question was actually asking. The question was, what dimensions maximize the volume? And so our answer is going to be to actually write out those dimensions. So, what dimensions maximize the volume? Well, let me just redraw the box. So we found that the depth should be 2 root 3. The width, remember, had to be twice the depth, so that must be 4 root 3. And we're left to figure out what the height has to be. Well, the whole point was that the height was determined by the depth. And if we scroll up just a little bit here, remember we found that h was 144 minus 4d squared all over 6d. So let's go plug in d equals 2 root 3 into that, or maybe it's even easier to just plug in root 12 into that. So h becomes 144 minus 4 times, well, 12, right? That's what root 12 squared is, divided by 6 root 12. So that's 144 minus 48 over 6 root 12, and now we just have to simplify things. So that's 96 over 6 root 12, which is 16 over root 12. Well, if you rationalize that, you get 16 root 12 over 12. So that's 4 root 12 over 3. And remember that the square root of 12 was 2 times root 3, so that's actually 8 root 3 over 3. So that's what the height is. Okay, so now we've actually answered the question. We've found the dimensions of the box that maximize the volume. If the question had asked us just what is the maximum volume, well, we would take these dimensions and multiply them all together. So just make sure you're actually answering the question. In any case, what we see is that once we took the word problem and translated it completely into just a math problem with a constraint and an objective, then it was solved in exactly the same way as the last one.